smash product of two spectra, well, at least for CW spectra. Let's see how to define the Hom spectrum. There are two ways. Well, the first one is just the straightforward one. We we take the nth component to be the space of all continuous maps from x beta n to y gamma n. But then we require that minus beta plus gamma should be n. What's the philosophical reason? Well, the philosophical reason is that C is covariant in the second argument, but contravariant in the first argument. And we also need to make sure that we, as n goes to infinity, we really go through all of x's and all of y's, because otherwise we cannot be sure that this thing knows everything about both spectra. So. Well, let's try to define the structure maps. And again, we may assume that n is not arbitrary, but belongs to some cofinal subset of z greater than or equal 0. So, for example, one could take as for the example, take A to be all even numbers and define gamma to be 3/2 n and beta of n to be 1/2 n. Why not? Okay, so let's see if we can define the structure maps. Well, let's remember that okay, here I need to let's start with this formula and let's see if the formula is correct. It's certainly correct if I replace the wedge product by the Cartesian product. Now, what happens if I what happens if I put on the smash product back in? Well, let's say x, y, and z are pointed.
Second, the map from X to the maps from pi to Z is also pointed.
Okay. So we have this this equality at least set theoretically, and if I replace spaces by CW complexes. And the spaces of continuous mappings by the compactly generated versions of the continuous mappings, then the formula the formula will be true without any further modifications. Okay, now let's see. Now what what do we want? by looking at this definition. What we want from this definition, we want to consider, we want to define the structure map. Well, to define the structure map, I need to either suspend this space and map it to the next one, or another option, I need to loop this to map this space to the loop space of the next one. Well, let's see which one of the two options is easier. Well, what is omega c x y? Well, again, let's put pt everywhere. So this we have by definition, and then we use the formula. So what do we get? We get CPT S1 cross y, no, S1 cross x, comma y. And now we're in business. S1 comma x cross y, or which is the same CPT x omega y. Oh yes, thank you. Yes, sorry. Okay, so basically, to define the smash product, it was easier for us to use the suspension version of the structure maps, but to define the Hom spectrum, it's easier to use the loop space version. This is definition 1. We will talk about definition 2 later. Okay, so I take f x y n, and I take omega f x y n plus 1, and I somehow need to construct a map from this space to this space. What do I do? Well, I know that this is C x beta n comma y gamma n, and this is what? And this is C x beta n plus 1 gamma n plus 1, and then when I put an omega in front, I get the same thing as and then we, by looking at this, we sort of know what we want to do. We want to use the map from this space to this one, which does exist. If gamma of n is 1 less than gamma of n plus 1. Okay, so our definition does not guarantee this. So we have this map. If gamma of n plus 1 is gamma of n plus 1. Okay, so this thing does not exist in general, but it gives one an idea of what to do. What do we do? Are there any suggestions? Yes, this is a good point. Let's think. So. The structure maps for x's are C x x plus 1 y to C sigma x n y. This is what happens when we take some particular n and hom everything into y. Very well. So this is the same as C x n omega y. Okay, so we want to use the structure maps for both x and y to go from here to here. Okay, so this exists, and beta of n equal beta of n plus 1. Okay, so okay, so let's think about the assumptions we need to make on beta and gamma, if any, in order to be able to define the structure map. And observe that the structure maps for the x spectrum decrease the index of the x spectrum, the index of the component. Well, let's think. Okay, so the structure map from the structure the structure map for y allows us to increase the second component by 1. The structure map for x allows us to decrease the first component by 1. Well, let's look at the indices and think a little. Okay, so we have C x. Let's go, for example, the first component beta prime, y gamma prime, and we have C. Okay. CPT. Beta double prime, y gamma double prime, and we want to see when we have a natural map from from the first one to the second one. Under which conditions on beta prime and gamma prime. I need a map from this space to. Let me write everything properly. So I need a map from this space to omega. I will write the degree in a minute. So omega CPT x beta prime prime y gamma prime. And then the number here has to compensate for the difference of the degrees, which is gamma double prime minus beta double prime minus beta prime, no, gamma prime minus beta prime. Okay, again, I will use another color in order to make this legible. So we have this space, and we want to see when we have a natural map from the first to the loop space of the second. And by the way, here we can put the loop space on the left and get again PT everywhere. CPT X N Y. Okay. My claim is this orange map exists when exists meaning we can construct such a map from our data. If gamma double prime is greater than gamma prime, and beta double prime is less than beta prime. Okay, let's see if this makes sense. Andrei, does this make sense? Sorry, Alexei. Andrei, Alexei, and Mikhail, and Jipping. Okay, just to make sure I remember everyone's names. Okay, so the claim is if we have if these two inequalities are true, then we have a natural map from here to here, which is obtained using the structure maps of both spectra. We pass from gamma prime to a larger gamma double prime using the structure maps of the second spectrum, of the Y spectrum. On the other hand, we pass from a beta double prime to a small, from a beta prime to a small beta double prime using the structure maps of the X spectrum. And we get we get the orange map. Okay, so it makes sense to assume that the gammas are increasing. Okay, let me put less than or equal, greater than or equal. If some of the indices does not change, well, nothing happens. Okay, so okay, so the it makes sense to so this definition makes sense if the gammas are increasing. Now the betas, on the other hand, need to non-increase, which is let's see if this makes sense. Okay, so the problem with betas non-increasing is that I can just replace everything by a point and up below a certain degree, and then this definition will give me a point. This is not what it's supposed to give. So let's see.
Maybe we need, in this definition, make it x minus beta 1, and that will go to minus infinity, but that doesn't really make sense.
Sorry, say again.
So if we make beta go to minus infinity, yes, it's so strange.
Well, if beta goes to minus infinity, then
It is c x minus beta 1.
так, у меня ощущение, что я где-то перепутал знаки, и из этого получается какая-то чушь. Но я не понимаю, где.
Strange suggestion. Maybe we should replace x by equivalent suspension spectrum.
Well, x may not be equivalent to a suspension spectrum, but it's a CW spectrum.
Yes, confused with omega spectrum.
So for an omega spectrum, x all all the x's will be all the maps we if y is an omega spectrum, then all maps we have here if y is an omega spectrum, then the maps of the first kind, which increase the number of the y component, are equivalences, and for the maps of this second kind, this doesn't really change anything. Okay, so let's think for one more minute, and if there aren't any suggestions, then this this will be this will be homework for all of us for next time. So once again, the problem is we do have maps, but we in order for them to work, we need the betas to decrease, in which case we or at least a non-increase, in which case we get a point basically for every way. Because for spectra, it's the plus infinity that matters, and the minus infinity doesn't matter at all. Okay, well, so this this definition didn't work. Let me say a few words about the other definition. Well, the other definition is the other definition uses Brown's representability for spectra. Definition number 2. Well, let's remember what we want to. This is what we want. Well, could we use this as the definition of f by z? Well, we could if we manage to prove that. So this can be taken as. of f y z if if the functor given by the left-hand side is representable. Well, basically, this is the definition of a representable functor. Now, now let me state the representability theorem. Well, to begin with, I will need to I need to define maps of degree n. Which are simply maps from x to y shifted by n to the I think to the right. So y minus n of k is yn minus n plus k. So, for example, the what was so the zeroth component would be the zeroth component of y minus 1 would be the minus one component of y. So shift to the right. Okay, now The maps of degree n, the group of the homotopy classes of the maps of degree n is denoted xyn. And I want to see which functors from spectra to abelian groups are representable. Okay, so. Так, Миш, вот сейчас мы сформулируем некоторую теорему, и вот это вот, значит, это и будет теорема Брауна, которая нам нужна в случае спектров. Suppose I have suppose I have a spectrum Y, and I take the in the homotopy category into Y. What properties does this thing have? Well, firstly, if I take the cofibrillation sequence for spectra, and I homoton to Y, and by the way, here I have the suspension spectrum, sigma A, the suspension spectrum, sigma A shifts everything to the left. For example, suppose I have the suspension spectrum of S1. It starts with S1. Its 0th component is S1. But the suspension spectrum of S2 starts with S2. Its 0th component is S2. So we basically take the suspension of S1, and we get S2 at the 0th place. Well, which means we have shifted everything to the left. So here I have 1 and not -1. And whatever I say should not be should not be taken as at face value. If you disagree, please let me know. Okay, so my claim is when I take hom into y, I get a long exact sequence. Okay, so the long exact sequence contains maps from A with a shift on the left and maps from A on the right. Now I want to say that these are the same thing, but here I want to put some index plus or minus 1 to make this correct. What do I put here? Plus 1 or minus 1? Okay, so let's see. A minus 1 got shifted to the left. So what used to be 0 is now in degree minus 1, and then I map the degree minus 1. So here I have a 0. A 0 in degree minus 1. I map it to y minus 1. So yes, I think the okay, so okay, so if I put y to the minus n or x of n, either of these gives me n, unless I've messed it up again. Okay, so we have a long exact, but whether it's plus 1 or minus 1, it doesn't really matter. We have a long exact sequence, and mapping into y gives me a long exact sequence. So this is the first property. The second property is is the wedge axiom. This is the same as a y minus 1. And well, I think this. Let me look at it again. I think this this is already. Okay, so I think this is already. This is already enough. So Brown's theorem if we have a functor from two abelian groups with with these two properties, namely, it takes a cofibration sequence to an exact sequence of abelian groups, which basically can be made long exact, but this doesn't matter at the moment. And secondly, it behaves well with respect to wedges. So any such functor is representable. Meaning it's given by homing into some spectrum. Well, now let's look at this expression, and let's assume Brown's theorem. So the basically the second condition is satisfied. It follows from the fact that firstly the smash product is distributive with respect to the sum or the wedge sum, and secondly we just use this. Okay, so the second condition is more or less clear. What about the first condition? Well, the first condition follows from the fact that if we have a cofibration sequence, then smashing it with Y, where this time Y is a spectrum, not necessarily a space, gives another cofibration sequence. Let's assume this for a minute, then we basically take a cofibration sequence, smash it with Y, get a cofibration sequence. Then we, from what we already know, and this is in fact easier for, this is in fact the easy fact about cofibration sequence, homing a cofibration sequence into Z results in an exact sequence of a billion groups. Okay, so we only need to check this, and I think basically we make an appropriate choice for both x, y, and for this Smash product to make sure this remains a cofibration sequence after smashing with Y. Okay, I think everyone's had enough of spectra for today. So let's leave this as an exercise, and hopefully next time we'll be able to clarify this issue with the first definition of the Hom spectrum. Are there any questions, comments? Well, then this is it for today. Well, we started late and we finished late, so.